Okay, so our next periodic table video here is on specific groups and sections of the periodic table. So we've learned about the general stuff. Now we're going to go into more specifics. So the first thing we're going to talk about is group one. These are the alkali metals. Okay, now group one actually has hydrogen in it as well, but hydrogen is not considered a metal, so it doesn't count as an alkali metal, but it's still group one. So going down the metals here, we have lithium, sodium, potassium, rubidium, cesium, and francium. All of the group 1 elements, including hydrogen, have one valence electron. And the alkali metals are extremely reactive. They are the most reactive metals on the table. Okay, so reactive that they will split hydrogen and oxygen apart in water and cause an explosion when they react with water. They're very, very, very soft, so soft you could cut them with a butter knife. However, we don't really find them in nature by themselves, not at all. They're really put together from compounds into their elemental form in a lab. Okay, so we're not going to find them out in nature by themselves. They'll be in a compound. Um, the compounds that they form are salts for the most part. Okay, and if you look at table salt, that has sodium in it. You look at bananas, they have potassium-based salts in there. You can also find the salts dissolved in things like Gatorades and stuff like that. When you hear the word electrolytes, you probably have some alkali ions in there. Hydrogen is not a metal, like I said, but it does have one valence electron. It is reactive, but for some different reasons sometimes. Um, it was used to make zeppelins float, but because it was highly flammable, there was obviously the major issues with things like the Hindenburg. So it's not really used for that anymore. But it can be used as fuel, and it does end up being a byproduct of a lot of different reactions. Group two: beryllium, magnesium, calcium, strontium, barium, and radium are the alkaline earth metals. These are similar to group one, but not all the way there. There's two valence electrons for this group. Very reactive, but not as reactive as group one. Soft, but not quite as soft as group one. They are also only found in compounds. They're not found by themselves. They are also found in salts. Uh, a characteristic that most of these have is that they're chalky to the feel and to the taste. Chalk itself has calcium in it. Limestone has calcium in it. Shells, calcium. Tums or other antacids usually have magnesium in there. Um, Barium, which does taste chalky when you drink it, uh, can be used in imaging for doctors. Going to go over the other side of the table here and look at group 17: fluorine, chlorine, bromine, iodine, astatine. Okay, these are the halogens. Okay, halogens means salt producer because they are going to react with group 1 and 2 metals to form the salts that we were talking about, right? Table salt, NaCl, it's got sodium and it's got chlorine in it. Okay, 7 valence electrons here, also very, very reactive. Fluorine and chlorine are gases at room temperature. Bromine is a liquid at room temperature. Iodine and astatine are both solids. Um, and we'll talk about that a little bit more as we talk about periodic trends, why that is. So, the compounds that these halogens make are often strong, caustic, poisonous, and irritating, which is why they're great for killing things like germs and bacteria. So things like bleach and pool cleaners and hot tub cleaners um, contain these kinds of elements. On the left, in the left picture, there is actually chlorine gas, which is extremely poisonous. The group right next to it to the right is the noble gases. I have a typo there. I just realized it. It should be Noble, not Nobel. They're not the Nobel gases. They're the noble gases. Sorry about that. But these are helium, neon, argon, krypton, xenon, and radon. They have what we call full valence shells. So most of these have 8 valence electrons, but helium has 2. And because of the full valence shells, they are inert, meaning that they do not react. Okay, inert gases. They're stable, whereas other elements on the table are not, which is why they want to react so badly. Okay, the noble gases are not going to react. There are some exceptions to that, but we don't really talk about them. They're often used in lighting. Okay, so like neon signs, and I believe it is xenon that is used in car headlights. Helium, as we know, is used in things like balloons and blimps because it is a very light gas, not quite as light as hydrogen, but still very, very light. In the middle of the table, from scandium over to zinc, is the transition metals. Um, Scandium to zinc and down, I should say, excluding the very, very bottom part of the table. These are tough metals with high melting and boiling points, except for mercury. Mercury is a liquid at room temperature and looks a little bit different as well than any normal liquid. Um, Most of these metals are grayish or silverish or brownish, although we know gold would be that bright yellow color. Um, but when they're in compounds, they oftentimes form very bright colors, as you can see in the pictures up there at the top right. Some other common examples you'd think of that: blood has iron in it, that's why it's red. Same idea with rust. Um, the Statue of Liberty, which was originally a brown color, is green because of copper reacting with oxygen in the air. Um, Other elements cause different colors as well. Many of the gems and um, precious stones that we use, things like sapphires and rubies, they're the colors that they are because they contain some sort of compound with transition metals in them. The transition metals can stand by themselves, but they can also be in compounds, like I said. Most of them have 2 valence electrons, some do have 1, um, just because they have some funky electron configurations that we're not really going to get into. If you take a look at group 11 specifically, you see copper, silver, and gold. These are the 3 best electrical conductors, which is why all wires are made from copper, silver, and gold. Gold actually being the best conductor of the 3. If you go to the very bottom of the table, to the part that we really haven't talked about much, you have the lanthanoids and the actinoids. So the top row there, from 58 to 57, excuse me, to 71, are the lanthanoids, excuse me, and they're just silvery metals, and we really don't talk about them very much. But the below that, the actinoids, we do end up talking about when we talk about nuclear chemistry because they are all radioactive. Uranium being the primary element that we talk about with the actinoids because of its use in nuclear power plants and nuclear weapons. So another, not really a group, but a list of elements that become important to us are the diatomics. Okay, di for 2, atom, atomic for atom, so 2 atoms. Okay, these are elements that only exist in twos. They will not exist by themselves as a single atom. So like O2 exists, but O by itself really doesn't. It will always be in some sort of compound if it's like that. So a way to remember them is Hofbrinkel. Okay, H for hydrogen, O for oxygen, F for fluorine, Br for bromine, I for iodine, N for nitrogen, and Cl for chlorine. If you notice, there are 7 of them. I like to call them the 7 because if you look at the picture on the right, on the periodic table, they make a 7, except for hydrogen. You just got to remember that hydrogen's up there to the top left. Okay, um, so I like to think of them as the 7. Okay, and that's it for our specific groups and sections of the periodic table. I know we didn't talk about all the elements. There are some really cool ones like carbon and silicon um, that we have not mentioned, but we will talk about them more extensively as we continue on with our understanding of elements, atoms, and their interactions with each other.